Hello everyone. So in our previous class, that was also an introductory class. We briefly discussed what all things we will be discussing in our course, right? So let's start discussing each one of the components, like each one of the things that we discussed in our introductory class in details. Okay. So let's start with the components of computer. Okay. So in previous class we discussed little bit about components of computer, right? So at least we know what all components are there in a computer, right? So a computer has CPU, a computer has main memory, a computer has IO devices, and a computer has system bus. Okay, so these are basic four components that a computer has. Okay, and what are the functionalities for these components? So what does CPU do? It is a brain of a computer and it performs the processing. Okay, it does all the processings that are expected from a computer. Okay, what is the functionality of main memory? A main memory acts as a storage unit. Okay, it acts as a storage unit and it stores special thing. What is that? It stores process. What is a process? Process is nothing but a program that is in a running state. Okay, and process has instruction and data, right? It has instruction and data. These are only two things that are present in a process, right? That means main memory stores instruction and data. We also sometimes call it as a program, right? So main memory acts as a storage unit. So the functionality of IO device acts as a user interface. It acts as a user interface. Okay, and so it takes inputs and it also provides the output, right? And system bus acts as a transmission media. It acts as a transmission media between whom? Between CPU, between main memory, and between IO devices. It is the one, like this system bus is the one that uh, that is used to communicate between different components. So CPU, if CPU wants to communicate with main memory, it uses system bus. So system bus is a transmission media. CPU wants to communicate with IO device, then system bus is used. System bus, because it is a transmission media, right? So so these are the four components of a computer. Okay, so let's start discussing each one of them one by one. Let's start with CPU. Okay, we also discussed little bit about CPU as well. Like CPU is logically divided into two parts, right? One is data path and second is control unit, right? Sorry. And like we also discussed that data path is considered as what? Technical team, right? Why technical team? It is considered as technical team because it is the one that actually does the operations, it actually does the task. So it performs task, and task is actually nothing but set of operations. Okay, task is nothing but set of operation. What exactly is operation we will be discussing. Okay, but for now you can just consider that data path performs certain task which is set of operations. Okay, now if data path performs the task, what does control unit do? So control unit is actually managerial team. So what do you mean by managerial team? So control unit manages things like it tells data path which task to perform and when to perform, which task to perform and when to perform. Okay, it sends signal, control unit sends signal to data path. Control unit sends signal to data path telling it two things, which task and when. So which task and when is also called as what when duo. Okay, what to perform and when to perform. Okay, control unit is the one which sends signal stating data path what to perform and when to perform. Okay, now let's start our discussion with data path. Okay, let's deep dive into data path. Okay. So what is data path? First question comes, what is a data path? So data path is actually nothing but a circuitry. It is a circuitry. We already discussed, right? Data path is nothing but a circuitry. Circuitry of what? Circuitry of hardware components. Okay, it is a circuitry of hardware components. And what does this circuitry do? It actually is a physical, or we can say hardwired implementation. So it is an implementation. It is an implementation of what? It is an implementation of what? Processing logic. Okay, it is an implementation of processing logic. Now the question arises, what exactly is a processing logic, right? What is processing logic? What is processing logic, right? Now so before understanding the processing logic, let me tell you one thing. So basically there are certain operations that are supported by a computer. Okay, so let's start with what we discussed in our introductory class. Whenever we were designing a computer, we defined what? We defined instruction set, right? And what is instruction set? Instruction set, sorry, it got executed, right? Whenever all these operations are performed sequentially, then we say that this particular instruction or the corresponding instruction got executed. Okay, now what is this processing logic? So since we have a certain set of instructions, right, that means, and each instruction has sequence of operations, right? For subtraction it will be something, load something, store something, but eventually we will be having some defined set of operations as well, right? Defined set of operations as well, right? And what does processing logic means? Processing logic here means, processing logic here means, it means the logic to perform the operations. Okay, this means that circuitry contains all the logic, like the logic of all the operations. Like if you want to perform this defined set of operations, circuitry will contain, this particular circuitry will contains logic for all the operations, okay, that are in the defined set of operations. Okay, now this okay, so it had, like, data path has A circuitry, data path is nothing but a circuitry, right? This circuitry has all the logics for like logic for all the operations, right? And control unit, control unit is the one that tells the data path, that tells data path, that tells data path which operation to perform and when to perform, right? When to perform, right? This means data path has the capability, it had the logic implemented inside it for all the operations. Control unit, whenever this particular operation is to be performed, control unit tells data path that perform this particular operation at this particular given instance of time. Okay, so let's take an example to make it more clear. Okay, so let's make a CPU board here. Okay, so let's consider this to be a CPU board. Okay, and sorry, CPU board. Okay, and this CPU board contains control unit, control unit, and anything that is not under inside control unit and is on CPU board, we consider it to be data path. Okay, anything that is not a control unit is a data path. Okay, that means data path will have certain hardware components: HC1, HC2, HC3, HC4, right, and so on. Okay, and all of them will be somewhat interconnected, right? All of them will be interconnected. It will also be connected to control unit, right? So this is how a data path looks like, a CPU board looks like. Okay, and let's suppose this is a main memory and there is an instruction. Okay, so let's try to fetch this instruction and execute this instruction. Okay, so how are we going to do that? So CPU fetches the instruction, it takes the instruction and gives this instruction to control unit. Okay, now what control unit does is it detects, it detects instruction. Okay, it detects which instruction is fed. Okay, that means whether this instruction was add instruction, sorry, was add instruction, was it subtract instruction, or what exact instruction this was. Okay, and after getting the information of the instruction, sorry, let me write it, instruction, right? So after getting the information of this instruction, control unit also has this entire definition, right? Definition of each instruction. What is the definition of instruction? The sequence of operations, right? So after detecting the instruction, it knows, control unit knows that, for example, instruction I1 requires operation OP1, OP2 and OP3 in the same sequence. Okay, so this is the sequence of operation that is required by this instruction. In order to execute the instruction, we will be processing, we will be doing this three operations in sequence, right? And suppose operation 1 can be done using hardware component 1, hardware component 2 can do operation 2, and hardware component 3 is capable of doing operation 3. Okay, so what control unit does is, what it does is, it sends hardware component 1 a signal that please do operation 1. It sends hardware component 2 the signal that says please do operation 2. it sends hardware component 3 a signal which says please do operation 3. Okay, so these are the signals that control unit sends to hardware components. Okay. And after getting these signals, hardware component does the task. It does the operation that is told to them. Okay, and and again, since we know control unit tells two things. What is that? First one is when to perform. Sorry, what? First one is what, and second one is when. Right? This two. So a control unit will send one signal for what and one signal for when, right? Therefore, each hardware component here, each hardware component will have these two signals coming from where? Coming from control unit. Each hardware component has at least two signals that comes from control unit. Okay, and one of them states what and other states when. Okay, so this what is mentioned on operation line. Okay, operation line, and when is mentioned on select line. Okay, so there are actually two lines that are connected to hardware component. One is select line, one is operation line. So let's erase it for a second and let's make it more clear. Okay. Let's make it more clear. Just a second. Yes. So let's again select one pen. So this is hardware component, and each hardware component is connected to the two lines, which is select line and operation line. Okay, and control unit tells this hardware component. So this hardware component is actually capable to do multiple tasks, multiple operations. Okay, it is actually capable to do multiple operations. Okay, so which exact operation is to be performed, this will be told by control unit through operation line. Okay, and when this particular hardware component will be working, in which particular tick this hardware component will be working, this will be told via select line. So what select line does is, whenever it is active, so whenever select line is active, that means to enable that enable the hardware component. Enable the hardware component. Whenever it is active, this means enable the hardware component for that particular tick. For that particular tick. Okay. For that tick. Okay, so which specific tick, in which specific tick this hardware component will be performing or doing something, that this will be decided using, this will be defined by control unit and sent as a signal via select line. Okay, so select line will tell hardware component, like select line, through select line control unit will tell hardware component when to get active. Okay, when to perform certain operation. Okay, I think till now everything is clear. So let's look into what are the different components, hardware components in a data path. Okay, so let me select a pen. So hardware components in data path, right? So there are basic three hardware components that are in a data path. Okay, so first one is register. Okay, first one is register. Second one is register. Second one is ALU. which is also known as arithmetic, arithmetic and logic unit, ALU, and the third one is CPU interconnection, CPU interconnection. Okay, so again the CPU interconnection is nothing but the wiring. Okay, so it is actually the wiring, or it is quite equivalent to system bus, that is it is a transmission media. Okay, sorry, it is a transmission media, okay, through which like the information passes. Okay, so register and ALU are the main components, register and ALU, and CPU interconnection are nothing but the wiring. Okay, but this wiring is actually very important because this plays an important role. It plays an important role in implementing the logic, right? Implementing the logic. How one register is connected to another register, or how one register is connected to ALU, this is how we actually kind of implement the logic, right? So wiring is very crucial part in implementing the logic. Okay, it also acts as a transmission media. Okay, so let's start our discussion with registers. Okay, so we are inside CPU, inside data path. Now we are discussing registers. Okay, let's continue. Okay. So so what are registers? What are registers? What are registers? So before discussing what exactly register is, let me give you an example here. Okay, let's understand this using an example. Okay, so as we know, CPU fetches instructions, right? CPU fetches instructions, okay, from main memory. And let's suppose the instruction sequence looks something like this. I1 is add a comma a. Now a here is actually a variable. Okay, variable that is present in data part of, so this is a process. Okay, this is a process, process P1. Okay, and this is also part of main memory. Okay, this process is inside main memory. Okay, and inside this process there is a sub part, data part, and inside data part there is a variable called a. Okay, suppose it is a global variable. Okay, add a and a. Instruction 1 is add a and a. Instruction 2 is add a and b. Instruction 3 is uh, add a and c. Okay, there is one more variable c. Okay, instruction 4 is subtract b and c. Instruction 5 is add a and b. Okay, now what you can, there is one thing that you should be observing, right? What is that? We are using this a multiple times here, right? Multiple times here. We are using b as well multiple times. We are using c as well, right? So there might be the case that uh, the instructions will use same variables multiple times, a b c. It may use many variables multiple times inside this instruction. Okay, while for processing, it might take the same variable multiple times for any kind of processing. Okay, so what happens is, like first instruction I1 is getting executed, right, by CPU. So what it does is, first instruction 1 gets into CPU, right? Now a control unit checks that it is an add operation, right? Now what it requires, control unit will know, right, that it requires variable a as well. So again CPU will fetch variable a as operand 1. Okay, now it will again fetch variable a as operand 2. So there are actually three fetch cycle. There are three fetch cycle. There are three fetches. There are three fetches in order to perform an execution. So I1 requires, even I2, I3, I4, I5, everyone, all of them requires, let me, yes. So all these instruction execution requires three fetches, right? Now these three fetches, what is the impact of these three fetches? So at each fetch, what it does, it waits for main memory to provides the information, right? And we also know that this main memory, the operating speed of this main memory is very low compared to the CPU. CPU's operating speed is actually very high, right? So if each instruction execute is very much dependent on main memory, right? If it is very much dependent on main memory, there is a bottleneck. So this thing acts as a bottleneck, right? It acts as a bottleneck because it will, like, instruction execution will wait for main memory to provide the information three times in order to do the execution, right? So it actually works as a bottleneck. Okay, so what is a, like, how can we work around this? So what scientists did was they provided CPU a kind of local memory that is inside the CPU. They provided CPU the local memory, or the memory units that are inside CPU, and these are called as registers. So registers are nothing but local sorry local memory units for CPU. Okay, and since these memory units are inside CPU, they are very fast. Okay, they are very fast. Registers are very fast to access. Okay. CPU can access these memory units in like in the speed of how it processes. Okay, with the speed of operating speed. Okay, so these registers are very fast. Okay, now there is an entire set of these registers. Okay, so we generally call the array of registers, all the registers, the array of all the registers as a register file. So register file is nothing but array of registers inside CPU. Okay, so register file is nothing but array of registers inside the CPU. Okay, so registers are basically the fastest memory unit of a computer. Okay, so actually any computer has many different types of memory units. Okay, main memory is one of them. Okay, and like we also discussed that there was secondary memory, right? The secondary memory, or IO device was one of the secondary memories, right? Secondary memory is an IO device, right? So secondary memory is one type of memory, main memory is one type of memory, right? Main memory is also one type of memory, register is one type of memory. So there are different types of memories, and we will discuss more about these types of memories and the memory hierarchy, depending on how fast they are and all those things. in memory organization, when we will be discussing about memory organization, we will discuss the type of memories, and we will also discuss we will discuss type of memories, and we will also discuss memory hierarchy. Okay, but for now, you can just uh, like consider a register to be, so actually registers are the fastest memory. Okay, registers are the fastest memory. Okay, fastest memory a computer can have. Okay, again we will look more into all those memory aspects in memory organization. Okay, so so this is kind of a logical representation of all the registers. Okay, but actually registers are not the array, right? The registers are not the entries of array. Actually register is a hardware component, so it looks something like this. Okay, so this is a kind of uh, the how a register looks. And a register has input line, it has output line, and two of these signal lines. We already discussed that all, since this is a hardware component, right? This is a hardware component, and each hardware component has these two signal lines coming from control unit, right? So it has select line and it has operation line. Okay, mentioning whether when exactly control unit opts this register to kind of enable, and which exact operation to perform at that particular time when it is being enabled, right? So yeah, this is register. So there are like only two operations that a register can perform, that is read and write. Again, you must be like we already discussed, right, that main memory supports two type of operations. We can do two type of operation in main memory. What is it? Read and write, right? CPU can do these two operations on main memory, right? And main memory is a storage unit, right? Again, register is also a storage unit, right? So only these two operations can be performed on register as well. So register will also be performing, oh sorry, CPU will also be performing only these two operations on register. Okay, read or write. Okay, so now let's see registers as a hardware unit. Okay, let's discuss more about this register. Okay, so logically register looks something like this, storing X bit of information. For example, this is 8-bit register that stores 8-bit information. Okay, but actually this register is nothing but a register. Let's uh, write the definition here. Okay, what is register? So register here is actually nothing but a group of what? Group of binary cells. Group of what? Group of binary cells. Group of binary cells that that operates side by side. Okay, that operates side by side to save set of bits. Okay, what does it mean? What is binary cell, right? What is binary cell? So binary cell is actually the most atomic entity inside a register, and it stores 1 bit of information. Okay, it stores 1 bit information. Okay, binary cell stores 1 bit of information. And we also know that all registers have some width, right? What does the width of register means? Width of register means the number of bits that it can store within it, right? So here we can say width of register is what? Number of bits register stores, or we can also say or we can also say number of binary cells that combinedly operates that operates side by side, right? That operates side by side. Okay. So width of register is number of bits this register stores, and since each bit is stored by one binary cell, therefore width of register is number of binary cells that operates side by side to make this particular register. Okay. Here we can observe that each binary cell here, like uh, this binary cell, this binary cell, since we called it atomic, right, that means they're independent in nature. All the binary cells are independent in nature, right? So therefore each binary cell has its own input bit, has its own output bit, and has its own signal bits. Okay. Select and read write. Read write is nothing but operation. Again, they come from what? They come from control unit. Okay. So yeah, it has input bit, it has output bit, it has select line, it has read write line, right? So it is independent in nature. Okay. Now the question comes, if they are independent hardware units, how they are grouped together as a register? Right? This is a common question, right? How are they like working together as a register? How is that, right? So we okay, let me use another page here. Let's consider binary cells 4, 5, 6, 7, and 8. Okay. So what happens is, since each of them has operation line and select line, and okay, we know that these binary cells should combinedly be a register, right? And each register will get one select line by control unit, right? Each register will get one select line from control unit, right? And we know that all of them are performing side by side, operating side by side. That means all of them will get activated at the same time, right? Therefore a common select line that is coming to register will pass through each of these binary cells. Okay. So this select line that is coming to register will actually pass through all these binary cells. Okay. And similar is the case with operation line, right? Because each binary cell will either read or write. Okay. And since they are combinedly working as a register, they will be doing either one of them and not both, right? This cannot be the case that binary cell 1 is writing and binary cell 2 is reading, right? So again, a common like a signal that is coming to register will be provided to all these binary cells. Okay. Because all these binary cells has their own operation line, right? So this is how they will be in sync, right? They will be getting activated at the same time, and they will be performing the same operation at the same time, right? Now how will the input and output work? Okay. Now each binary cell will get one bit of information, right, as an input, right? And it will give one bit of information as an output, right? Like this, right? Now what is the sequence here? Okay. So the sequence is something like this. Okay. If it is having, So suppose like here it is 8-bit register, right? It is 8-bit register, 8-bit register, right? That means 8 input lines will be there, 8 input lines will be there, and each input line will provide one input to this register. Okay, and that eventually means that 8-bit register will store 8-bit of information, right? The input will be 8-bit of information, input will be 8-bit of information, and 8-bit of information will be in binary sequence 1011101111, something like that, right? And this has some meaning to it, right? So the leftmost binary cell will contain or will save, will get, it will get most significant bit. Okay, the leftmost binary cell will get, this will get the most significant bit, whereas the rightmost binary cell will get least significant bit, least significant bit. So for example, this is a sequence, right? So if this sequence is coming as an input, then this is least significant bit, sorry, this is least significant bit and this is most significant bit, right? Okay, so for those who don't who are like new to most significant and least significant bit concept, let me give you an idea in brief. So for example, if we have some sequence, like this, 3 4, okay, something like this, then it represents something, right? So let's suppose it represent a number. Okay, so let's suppose it represent a number. So each of these bit will have some weightage associated with it, and the rightmost bit will have weightage 1. Okay, the one in the second, like from the right, will have weightage 2, and it will keep on increasing by a multiple of 2, like 2 to the power 1, this is 2 to the power 2, that is 4, similarly 8, similarly this is 16, 32, 64, 128, right? So this will the weightage will increase towards left by a multiple of 2. Okay, that means the bit that is on the leftmost side will have most significance, right? Because why? Because it has the highest weightage, what we do normally, like if this is a value, how will we convert this sequence into decimal? We will multiply it with the weightage, like 128 into 1, and do the summation, plus 64 into 1, and so on, up to plus 0 into 1, right? And this is our value. Suppose this is x. So inside x, the highest weightage, the bit with the highest weightage is the leftmost bit, right? Because the weightage here, the value that is multiplied to this particular bit is highest here, right? So therefore this leftmost bit is called as most significant bit. Okay, and the rightmost bit is called as least significant bit, least significance, because it has least significance. Okay, it always has the weightage 1. Okay, so here whenever any input sequence comes, the most significant bit goes to the leftmost binary cell, and least significant bit goes to the rightmost binary cell. Okay, and this is how it gets the input, and this is how it provides the output. Okay, I hope this makes sense. Okay. So now this is how each binary cell like all the binary cells are grouped together and they perform or operate as a register. Okay, so now what we will be doing is we will be discussing a little bit about binary cell. So this binary cell, all the binary cells here are actually implemented using JK flip-flop. Okay, so let's discuss little bit about JK flip-flop. But again, this is a note that JK flip-flop, you will be reading about JK flip-flops in digital logic course as well, and this won't be asked like in details as to how JK flip-flops are actually, how they're actually used in registers. So but let's have a quick discussion on this, because like it will be beneficial for you, right? Because it is better to have some knowledge of how things actually work, right, compared to just mugging all the functionalities, right? So let's have a quick look at JK flip-flop, how JK flip-flop are are used as binary cells. Okay, okay, so let's start. So I think everyone knows, or at least they will study, that JK flip-flop acts as a storage unit. Okay, it acts as a storage unit, and it stores one bit of information. It stores one bit of information. Okay, it acts as a storage unit and it can store only one bit of information. Okay, now how do this JK flip-flop stores the information? Okay, so let's look slightly into the structure here. So JK flip-flop looks something like this. So it has two input units. It has two input lines, sorry, J line and K line, and it has one output line, that is Q line. Okay, it is also connected to a clock. Okay, now this clock works exactly the same as we discussed in the this introductory class, right? Tick by tick, tick by tick, right? It will be having these kind of signals, and the start, the rise of each signal represent one tick. So this is T1, this is T2, and so on. Okay, and what JK flip-flop does is, okay, it works tick by tick. That means at tick T1, what it does, it takes value J, sorry, the input that is provided through J line, and the input that is provided through K line. For example, it is small j, it is small k. It J can be 0 or 1, and K can be, small k can be 0 or 1. Okay, so yeah, so J and K, uh, it will it will take value small j, small k at time at tick T1, and it does some operation on that. What exactly is that operation, we will discuss. Okay, it does some operation on that, and it generates an output. Okay, this output is then put, let's suppose this output is q, small q. Okay, now this output is put on this output line, big Q. Okay, so this acts as a output, small q. Small q is again a bit. Okay, q can be 0 or 1. Okay, now between time tick t1 and tick t2, it will keep on providing this value small q on the line. That means, in a way, we can say that between tick t1 and tick t2, it stores the value q, right? It stores value q between tick t1 and tick t2. It stores the value q. Now at tick t2, it again takes new j and k and does do the operation, and generates new q dash. Okay, and sends this q dash to the result line, that is big Q. And now from tick t2 to tick t3, this new value q dash will be saved. So it stores one bit of information tick by tick, tick by tick. Okay, tick by tick. So what is the concept here? If we want to store, if we want to store some bit, for example, q here is 1. Let's suppose q here is 1, and we want to store this value 1 for more than one tick. Then what we do is we provide the value inputs j and k in such a way that value q keeps on getting stored, or the result that is generated will always be value q for for tick t1, for tick t2, and so on, till we want this value to be present inside the this particular flip-flop, right? I hope I am making sense till now. Okay. So JK flip-flop stores one bit of information tick by tick, and in order to store any bit for certain duration, we just provide the input accordingly. So what information, like what input is to be provided in order to save this queue, is what we will discuss a little bit. Okay. So let's again take some example here. uh, let's suppose at tick t minus 1, at tick t minus 1, the value, let's suppose there are two scenarios, scenario 1, sorry, scenario 1 and scenario 2. Okay. And at tick t minus 1, the value of q, that is the value stored at tick t minus 1, let's suppose it to be 0 in scenario 1 and 1 in scenario 2. Okay. This is tick t minus 1. Okay. Now this is past actually. Now let's discuss about tick t, the current tick. Okay. And again, it again depends on whether we want to continue with this value or not, depends on the value at j and k. So we consider the inputs to be j and k here. Okay. And there are only four combinations possible, right? j and k are input here for a jk flip flop, and there are only four possible combinations. What are those? 0 0, 0 1, 1 0, and 1 1, right? Now this is q at time t. So what is it? What will be the new q, new qt? If it changes, if it changes from qt minus 1, that basically means that our value has been written. Our value has been written. Okay. So write means q qt minus 1 may or may not be equal to qt, right? And read means if we read, that means if we store, sorry, store, not read, store. If you want to store, that means qt minus 1 should be equal to qt. Okay. So so if j and k, j equal to 0 and k equal to 0, this is that scenario where the value will be same as qt minus 1. This means that if the scenario 1 was there, that means qt minus 1 was 0, then qt will also be 0. Similarly, if qt minus 1 was 1, then qt will also be 1. Okay. This is scenario 1. This is this is the first combination, right? This first combination says 0 0 says remains same, and this combination is basically used to store store bit for longer duration, right? For longer duration, store bit for longer duration. Now this store, this is done when j is equal to 0 by giving j is equal to 0 and k is equal to 0 as an input. Okay. Anything other than this, let's discuss. Let's suppose j is equal to 1 and k is equal to 1. So in that case, how a JK flip-flop works, it actually toggles. That means if the value at qt minus 1 was 0, it will toggle to 1. If value was 1, it will toggle to 0. That means it is just the opposite of qt minus 1, right? It is just the opposite of qt minus 1. It is complement of qt minus 1, right? Okay. uh, so these are the, like, this is remains same, and this is toggle, right? What if j and k are not equal to 0? What if j and k are not equal to 0? Okay. What if j and k are not equal to 0? Okay. Not equal to, sorry, not equal to each other. I'm so sorry. What if j and k are not equal to each other? That is, if j is equal to 0, then k is equal to 1. If j is equal to 1, then k is equal to 0. Then what happens is, irrespective of what, like, irrespective of what k is, actually k will be just opposite of j, but the value of qt will be j. Value of qt will be j. That means j is equal to 0 here. That means j will be 0 in all the scenarios. If j is equal to 1 here, that means qt will be, I'm so sorry, qt will be 1 in all the scenarios. Okay. So yeah, this is uh, kind of table which I just showed here. This is the same thing, right? Whenever there is the clock is 1, that means there is some tick. For example, we discuss about tick tick. Whenever there is a clock and j and k has different combination, like out of which exact combination is coming through j and k will decide what will be the value of q. And that means that what will be, it defines whether we will be proceeding with the value which was previously there, or we will be writing the value or the bit inside jk flip-flop. Okay, so this is actually how JK flip-flop works. So it what it does is, it actually supports JK flip-flop supports writing, write, okay, and supports store, right? And this is what we require from a memory, right? This is what we require from a memory. It should be able to store something, and we should be able to, and we should be able to write it, right? Whenever we want to write something onto this particular unit, we must be able to write it. Okay, so these are the two things, criteria, that should be followed by any memory unit, right? So this is being followed. So it is a green flag, like we can use JK flip-flops as a binary cell, right? Now the question comes, so you must have seen binary cell, right? We just discussed binary cell. Binary cell actually looks something like this. It has one input unit, one input bit, one input line, it has one output line, it has select line, and it has operation line, right? Operation line and select line. It does not look like JK flip-flop, because JK flip-flop actually has two inputs, right? Two inputs. It does not have select and operation lines, right? It has two input lines, but binary cell, our binary cell has just one input line. So actually what happens is, so this binary cell, our binary cell actually looks something like this, right? It looks something like this. But since JK flip-flops are used and they kind of support all the things that are required by binary cell, we build a circuitry around this JK flip-flop so that it takes only one input, and it takes one select line, it takes one read or write line, and it gives one output. This is the circuitry. Okay. Again, this is a note that this circuitry won't be asked. Okay, this won't be asked, but I would highly suggest you, I would highly recommend you to take out some time and try to dry run, like by providing some values, since input can be zero, either 0 or 1, select can be either 0 or 1, read write can be either 0 or 1. Here 1 means here uh, read, and 0 here means write. Okay. So I would highly recommend you to dry run and provide all these combinations one by one and see how this entire circuitry works. Okay, this will be like a homework for you, and please try to like understand how this circuitry works. Okay, this will give you a very good understanding of how our binary cell, or how a binary cell works. Okay. So this is a binary cell. Okay, this is all about binary cell. Okay, so I think everyone here is now able to visualize how binary cell actually looks on a hardware level, right? This is how it looks on a hardware level. Okay, now let's go again up onto this register. Like let's again discuss about registers. Again, we also discussed this part, right, where we saw that this is the logical version of register, and actually the hardware, how actually this register looks. It looks something like this. Input lines, here there are 8 input lines, here there are 8 output lines, and each binary cell will store information or 1 bit according to the placement, right? Most significant bit will be stored in the leftmost binary cell, and least significant will be stored in rightmost binary cell, right? And control unit, when it sends signal, these two signals, select signal and operation signal, it sends the signal to register, and register will kind of send this signal to all the binary cells combinedly, right? We have already discussed that, right? So now we also have kind of a, like, we can visualize how actually a register will look on motherboard, right? On the CPU board, right? On a processor. So this is how our register looks. So so this is all about like implementation and working. Now let's discuss the type of registers that are generally there in any CPU. Okay, so there are basic, like the type, there are many types of registers in CPU. Okay, and these types are basically categorized based on two aspects. Okay, based on two aspects. What are those aspects? Those aspects are information they store, information that the register store, and the task they perform. Okay, task performed, per sorry performed. So like type of they are categorized, each register is categorized based on these two things: information they store and task they perform. Okay. So let's start discussing the register types based on information they store. Okay, so data register, there are basic two types of registers based on information they store: data register and address register. I hope the name already is giving you an idea. So data register basically stores data, right? Whereas address register stores addresses. Okay. Now what is data here? Data with respect to data register is actually instruction as well as variables, which again we call data, right? Variables. So data register can store either instruction or variables. Okay, it can store both of them. Okay, data register can store data, but data here means instruction as well as data like variables. Okay, and what exactly address here means? Address here means the address of either the cell of memory, main memory, cell of, okay, cell of memory actually, because register file was an array, right? Let me go to, yeah, a register file was actually array of registers, right? And actually each register has some address to it. So this actually has some address a1, it has, this one has some address a2, and so on. Okay, registers also have addresses. Okay. So address register stores the addresses of cell of memory. Okay, cells of memory, it can be main memory or it can be a register. Okay, or cell of register file, it is the same thing, right? Or it can be the address of any IO device. It can be the address of any IO device. Okay, it can be either of them, either the cell of memory or the IO device. Okay. So what should be the width of these registers, like data register and address register? Okay, so let's discuss about the width of both the register, both the types of register. What are those? Data register and address register. Okay, so let's start with a width of data register. Okay, width of data registers. So first of all, what are the things it stores? It stores instruction and it stores values, right? It stores instruction and values. Now these values can be either absolute values or it can be variables, right? Our program generally contains both these things, absolute values and variables, right? Absolute value is something like 5, 6, 5, 10, something like that. Variables are something that we initialize and we use, right? Something like x, y, x, j, y, something like that. Okay. So now data register stores instructions and values. Okay. Now the question comes, if data register stores instruction and values, where where does the data register get this instruction and values? We also discussed this, right? So instruction and values are basically present in main memory, right? We have this entire process and this process contains what? Instruction and data, right? Let's put it v. Okay. Okay, so now the question comes, what is the width of data register? Okay, so first of all, let me tell you one thing. So instructions, let me choose another. Yeah, so the instruction are basically of two types: fixed length and a variable length. Okay, it can be fixed length and it can be variable length. Why am I telling you this? Because we need to know that instruction can't be fit into one register always. Okay, so we might need more registers in order to store one instruction. Okay, and one instruction can be present in multiple cells. So for example, sorry, cell X contains instruction I1, cell X plus 1 also contains instruction I1, and X plus 2 also contains instruction I1. So this can be the case. Okay, okay. So again, so if the length is variable, how do we store it in register? So what should be the width of the register, right? Because we can't change the width of register all the time, right? Based on the length of instruction. So we use the property of fetching. Okay, so we know that we fetch instructions, right? And while fetching the instruction, we get instructions where we get instruction via data line, right? We get instruction and values both via data lines, right? And we also discussed that one unit of information, we consider one unit of information to be one word, right? One word is nothing but one unit of information. And what is one unit of information? It is one unit of information is one word, right? Number of data lines is one word, right? So what we generally do is we take the width of data register to be one word. Okay, so mostly all these processors, they have the registers of width one word. All the data registers have one word of information, like one word of capacity, and one word of information can be stored in data registers. Okay, it makes sense. I think it makes sense. Okay, now what is width of address register? Width of address register. Okay, so okay, let me tell you one more thing. For example, uh, if instruction is like bigger than one word, there, for example, it is three-word instruction. Instruction is three-word instruction. Then we can have our instruction, like we can get the instruction in chunks, like it can be fetched from, it can be stored in one chunk can be stored in R1, second can be stored in R2, third can be stored in R3, and combinedly we considered R1, R2, R3 as one instruction. Okay, information stored in R1, R2, R3 as one instruction. Okay, so basically one word is nothing but like the width of data register is one word. Okay, now what is the width of address register? So the first thing that will come in your mind is address of register, like width of address register must be what? Must be number of address lines, right? Sorry, number of address lines, because like number of address lines are nothing but it kind of states how many bits are required to represent an address, right? And if we are storing any address, we require only those number of bits which are required to represent an address, right? Therefore, address register, the width of address register can be number of address lines, right? Okay, but what we generally see, uh, like practically, is in order to generalize the registers, in order to make registers useful, like make register general enough to make it store data as well as addresses, they are having width of same width. Okay, they are having same width, but they can have same width only when let me take another pen. Yeah, only when number of address lines are less than number of data lines. If number of address lines are less than number of data lines, in that case a width of in that case a width of address register is one word. Okay, since number of address lines are less, therefore we can represent, we can store any address using a small part of a register, right, whose width is one word, right. We can just put the padding in the front or in the back, and just use these registers, data registers, as address registers as well, right. And why we are making this kind of exception, why are we trying to generalize data and address registers, uh, this is because, like we will discuss, so this is generally because we have some general purpose registers, and general purpose registers can store data as well as address. So if we store data as well as address, the width of that particular type of register should not be dependent on either the length of address or the length of data, right. Therefore, in order to resolve that, we try to make the width of address register to be one word as well. That is the case when number of address lines are less than number of data lines. But if if this is the case, like if number of address lines greater than number of data lines, we can't do anything, right? Because we need more bits in order to represent an address, right? In that case, width of address register is same. What? Number of address lines. Okay. Width of address register is number of address line. So there are two possibilities. If number of address lines are less than data lines, in that case width of address register is one word. Okay. And if number of address lines are greater than number of data lines, in that case width of address register is number of address lines. Okay, which will eventually be more than one word, right. Okay, so I think I'm making sense here. So we discussed width of data register as well as width of address registers. So let's proceed. So the width of data and address registers will be same. We will discuss what is the benefit of that as well, okay, in just some time. So let's proceed our discussion. So another type of categorization is based on the task they perform, based on the task assigned to them, that is the task they perform. Okay, so there are basic two types of registers: general purpose registers and special purpose registers. Okay, again the name suggests general purpose, special purpose. What does it mean? It means that general purpose registers don't have any purpose, right? They don't have any, they don't have any predefined functionality. They don't have any predefined functionality. Whereas special purpose registers, as the name suggests, do have, they do have predefined functionalities, right? They have predefined functionalities. Okay. So okay, so okay, one way to visualize general purpose register is they are kind of like uh, additional registers additional registers additional registers that are present on CPU, and CPU provides, or CPU defines the task or gives the task to these additional registers on the go based on the requirement. Okay, CPU will give the task to these additional registers based on the requirement. Okay, therefore, therefore, additional registers. Let me use another. Okay. Therefore, additional register can store can store can store both data as well as addresses, right? Now the additional registers can store data as well as registers. Now we are like seeing the benefit of having width same for data registers as well as address registers, because here if address registers were having if address registers were having different size, then it will be kind of different, kind of hard, right? These additional registers uh, would have split into two, one for data, one for address. Now any register can be used for any purpose to store anything, right? Now, I mean, this general purpose registers can be used to store data as well as address. Okay, this is their functionality. Okay, they also follow a nomenclature. Okay, each general purpose register follows a nomenclature. They follow a nomenclature. Okay, they follow nomenclature. What is that nomenclature? Okay, so whenever we, okay, general purpose register is also written as GPRs in short. Okay, general purpose register, GPRs in short. So GPRs have a nomenclature, something like R, R followed by an integer. Okay, something like R1, R2, R3, and so on. So whenever you find any register being called as R1, R2, or any R any R followed by an integer, just consider them to be general purpose registers. They all are general purpose registers. Okay, and all the special purpose registers, they are actually having certain names. They are not like R1, 2, 3, something like that. So all the special purpose registers are having name that are not similar to that of R followed by an integer. So whenever you get any register name with something like this, with nomenclature like this, just consider them to be general purpose registers. Okay. So yeah, this is all about general purpose registers. Now special purpose registers. Okay, again, special purpose registers already have their predefined functionalities. They have certain predefined functionalities, right? Therefore, they can store either data or address, but not both. Data or address, but not both, right? But not both. And based on the functionalities, they will be storing the information, whether it can either be data or it can be address, but not both, right? Because functionality is already predefined, right? And in any CPU, in any CPUs nowadays, there are 9 basic special purpose registers that are present. So what are those 9 special purpose registers? These are those 9 special purpose registers. Okay, there is you can just see there is a color scheme for 4 of them and 5 of them. The one which are written in green actually are address registers. Okay, they actually are address registers, whereas the one which are written in blue are actually data registers. Okay, so four of them are address registers that stores addresses, and five of them are data registers that stores data. Data means instruction or variable. Okay, now we will be discussing each one of them in great detail in our next class. Okay, so we will be discussing all of these nine special purpose registers in great details in our next lecture. Okay, thank you.